Okay, AP students, we're going to do a little video lesson here on a concept called apparent weight. And so as we go through this, I'm going to have you use this worksheet that you picked up in class today, and we're going to use that for the examples. Let's just start off by kind of focusing in on the definition of apparent weight. And apparent weight is defined as the normal force of the floor that pushes up on you, okay, when you're standing on the floor. N is what a bathroom scale would read in newtons, and this is called your apparent weight. So maybe that sounds kind of odd to you. It's like, of course it is. If you stand on a bathroom scale, your bathroom scale is going to measure your apparent weight. But what you have to imagine is what happens if you were to actually be standing in an elevator, where the elevator suddenly accelerates upwards while you're standing inside. You've probably noticed the feeling of briefly feeling heavier, and what you're feeling is actually the normal force of the floor pushing up harder on you briefly as the elevator accelerates upwards. Now, we would say in that case that your apparent weight actually is higher than your usual weight equal to mass times gravity, because the floor has to push up on you with a little bit extra force in order to make you accelerate. So apparent weight is actually not equal to mass times gravity. We say that it's equal to the normal force of the surface against you, and that can change. So let's take a look at how that relates to Newton's second law and net force. The net force on you, if you are standing on a floor, is going to be equal to the normal force going up minus your weight going down. So that would be normal force minus mg. And the combination of these two forces over here are going to be equal to your mass times acceleration. Okay. So we're saying that the apparent weight is actually this force right here, this normal force. That's your apparent weight. And so if you were to rearrange this formula, right, by adding mass times gravity to both sides, add this term to both sides, you would find that your normal force is actually equal to your mg weight plus ma, where a is just the acceleration of your frame of reference. Okay, so if you're in an elevator car, your frame of reference might be accelerating up or down, and that's the acceleration that you have to worry about. So let's make this a little more real and look at some different cases here. Let's start off with the most basic case of just, having a person stand in an elevator, and let's say that the elevator has a constant velocity up or down. Okay. You could also say, or it's at rest, right? So it could be at rest too. And the bottom line is that if it has a constant velocity, or if it's at rest, the acceleration is going to be 0 in both cases, so 0 meters per second squared. All right, so let's look at the person here, okay? And I put a dot on the person's body. We're going to just draw the free body diagram of the person. So the person has a certain weight, which might look like that. And common sense would tell you that if the elevator car isn't moving, the normal force is going to be equal and opposite to the weight. So the free body diagram looks like that. Of course, these two forces cancel, and you don't have any acceleration. Okay. So what would your apparent weight be in this situation? Okay, can you think of that? What would it be? Probably it would just be equal to your normal weight, the weight that you typically feel. Okay, so let's come back and use our definition here, and the apparent weight is going to be equal to mg plus ma. And in this case, it's just going to be mg plus 0 because there is no acceleration. Okay. So let's see, for a person who has a mass of 50 kilograms at 10 meters per second squared for g, your apparent weight would be 500 newtons. Okay, and that's just what your usual weight would be, your mg weight. And we would say that in this situation, a person is experiencing what we would say to be one g-force. Sometimes you hear that term g-force. That just means that you're experiencing your apparent weight is equal to your mg weight. Okay. All right, let's look at a more interesting case here where you actually accelerate upwards at some rate. Okay. So accelerating upwards, let's make up a number here. Let's keep it simple. Let's say you accelerate upwards at +1 meter per second squared. Okay, so you're in this elevator car. Now, in order for you to do that, the normal force has to push harder on you. So I'm going to draw my weight vector the exact same way as I had it before, but I'm going to now make the normal force a lot bigger. Kind of exaggerate it. So now you have a net force going in the upwards direction. Now, before we calculate your apparent weight, think about it. How do you feel when you're in a car which is accelerating upwards? You should feel a little bit heavier as it accelerates. Apparent weight, we would expect to get something which is going to be bigger than 500 newtons. So let's see what it works out to be. Normal force is going to be equal to mg plus ma. And here we have 50 times 10. But now we have to add this other term, 50 times 1. So we end up with what? 500 plus 50. And that means that your apparent weight in this situation would be 550 newtons. Okay. Now, if you look at the ratio of 550 to 500, that's a ratio of 1.1. And so we would say that in this situation, you're feeling a g-force of 1.1 g's because you feel heavier by a factor of 1.1. You're not really heavier, but you feel that normal force pushing on you harder. Let's do another case. What if you're accelerating down in the elevator? So let's make the acceleration negative 1 meter per second squared. I'm going to start with my FED. Again, I make my weight vector the exact same as before, but now the normal force, I'm going to make it really small. Kind of exaggerate it there. And I hope you can see that there is now a net force which points down. Okay, so prediction, how are you going to feel in this situation? This is kind of one of those, you get like a light weight feeling. Maybe your stomach feels like it's lifting up. So your apparent weight should be less than 500 newtons. So it would be 50 times 10 plus 50 times negative 1. So we've got 500 minus 50, that's 450 newtons. Okay, so if you were standing on a bathroom scale, the bathroom scale would actually read a little bit slightly lower number. And that ratio of 450 to 500 is 0.9. So we would say that you're at 0.9 G's there. Okay, so you feel like your weight is about 90% of what it usually does. Last cases are really extreme, and I hope you're never in these situations in real life. What happens if the cable snaps on the elevator car and you just are in free fall? In that situation, unfortunately for you, weight is still acting on you, but nothing else is. So there is no normal force at all. And your acceleration is going to be negative 10 meters per second squared. So you're just dropping. Now, can you predict in this case, how hard is the bathroom scale going to push up on you if you're just in free fall? The answer is it's not. There's not going to be any push. So our normal force here is going to be, I'm not going to write the formula again, but it's going to be 50 times 10 plus 50 times negative 10. And of course, those cancel each other out. And so in this unfortunate situation, you're in trouble. And you're in a 0G situation. Okay. Now, this does not always result in death because right now there are astronauts in the International Space Station who are doing exactly this, and they're perfectly fine. They're basically falling towards the Earth. And the reason that they don't crash into the Earth is because they're moving so fast sideways that they never can reach the Earth because the Earth is curved. So they're falling, but they're also kind of wrapping around the Earth. So, astronauts in space, they have a lot of mg. They have a lot of m times g because g is pretty strong up where the space station is. But there's no normal force underneath them because they're falling. And so their apparent weight is actually 0. So astronauts are not really weightless in the International Space Station. They just have an apparent weight of 0. Last case is going to be kind of a bizarre one, but what if you took the elevator and you put a rocket on it so that it accelerated you downwards faster than gravity would normally have you go? Let's make up a number here and make it negative 15 meters per second squared. So in other words, if there was a race between you and someone that dropped something, you would accelerate more than an object which is just falling. In this case, something interesting is going to happen. Your head's going to hit the top of the elevator car, and now the elevator is going to have to push down on you to help you to go accelerate that much. So your free body diagram is now going to be your weight. Oops, kind of overdid that one. Your weight, and you're going to have another force. I'm going to draw it here off to the side. That's your normal force. And so the normal force is actually happening because your head is touching the top of the car. And so now these two forces combine to drive you downwards. So how hard is the car pushing on you to make this happen? Maybe you could stop and take a guess as to how many newtons that's going to be. Let's check it out. So you're going to have the usual 500, but then you're going to have also this negative 15 here. So plus 50 times negative 15. And when you do the math on that, you get negative 250 newtons. Okay. So what you're experiencing is that the elevator roof is pushing down on you with that force. That's why it's a negative number here. Okay. And in this case, you would be experiencing, I guess, what we would call negative half g, because the roof is pushing down on you with half of your weight in the negative direction. Okay. So this is a consideration on roller coasters, because in some roller coasters, the ride itself has to push down on you to hold you in the seat. Maybe there's a seat belt, maybe there's a shoulder harness or something like that. But in that case, you need that shoulder harness to push you down, otherwise you would go right out. Okay. So hopefully that makes sense, and just kind of putting things together here. All of these systems that we're talking about, at least the last 4, have to do with acceleration, right? And if you're in a frame of reference that's accelerating, then whatever surface you happen to be resting on is going to exert either more or less force on you to make you accelerate too. And the apparent weight is a measure of that. Okay, so please have a shot at some of those problems I posted and see if you can figure those out, and we'll check in tomorrow.